Okay, so thank you for the invite to talk, and thank you for everyone who's been running the hands-on sessions and put most of the effort into getting a great program for this workshop. So I feel there's quite a lot riding on my shoulders because the title of the workshop is Microlensing in the Era of WFIRST, and this is kind of what my talk is all about. So I should say before starting that the Microlensing survey on WFIRST is due in large part to the years and years of work by Dave and Scott and various other people who have contributed to the numerous proposals that went into work out all the kinks in this kind of survey design, and then also, of course, it's thanks to all the people who have worked on all the other aspects of WFIRST and the predecessors. So I'm going to go through the outline of my talk. I'm going to spend a fair bit of time just doing an order of magnitude estimate of how you would design a microlensing survey, either from the ground or from space, to look for planets, and then once I've done that, I'll go on to describe the WFIRST survey itself and the science that you might do with that. And then at the end, if I have time, I'll point out some projects that anyone in the audience might be able to work on, but we haven't really looked at yet. So if we set ourselves the goal of finding 100 Earth mass planets, this is a good number for doing statistics, then what survey do you need to achieve that? So the first thing to think about is the detection efficiency of microlensing. So if you look at the left-hand side of this magnification map, we saw plenty of these earlier in the week. You can see the caustics of a Jovian mass planet very easily here. But you might not notice the caustic of an Earth mass planet down here. I don't think this is even an Earth mass. This is, I think, 5 Earth mass planet. So as also discussed earlier, the detection efficiency is basically the probability that your source trajectory through this magnification map will encounter one of these caustics. And so for ERPS, I think this was first calculated by Bennett and Ree. Maybe the first papers saying that you could detect planets with microlensing covered this a little bit, but it was Bennett and Ree that first went through the detailed calculations for planets this small. I think I've got the year wrong there. It should be probably 1996. And the number they came up with, if you observe continuously at high enough cadence, etc., is about 1%. So if you want to detect 100 Earths, you're going to need to observe 10,000 microlensing events. So how do you find 10,000 microlensing events? To go through this, we need to go through a couple of basic concepts when it comes to microlensing surveys. You want to compute the rate at which events occur, but just before we do that, there's a slightly simpler concept, which is the optical depth to microlensing. So this is the probability that at any given time, a star that you're looking at is being microlensed. And so you can compute that just by adding up the area of all the Einstein rings that from all the lenses along the line of sight to that given star. And in the case of if you had high optical depth, like this picture of bubbles on the right, then you'd have a high chance of having a given star being microlensed. But just the scales involved, the angular Einstein ring radius is a milliarc second, so the area is microarc second squared. and then you compare that with the number of stars that you have, even in the densest part of the galaxy going towards the bulge. You get some large numbers multiplying by some very, very small numbers, especially when you think about it in terms of square degrees. And then you get a result which is not what I've put here. There should be a minus sign on this 10 to the 6 here. So the probability that any star is being lensed at this given moment is about 1 in a million. So the event rate is slightly more complicated. So rather than just having a static picture, now everything is moving. So you want to know not whether a star is being lensed right now, but how often will any given star be lensed. So you can compute that just by computing the area that's swept out by the Einstein rings as the stars and lenses move. And you can do this at an order of magnitude level just by taking a typical Einstein radius and then multiplying that by the typical proper motion typical relative proper motion between lenses and sources. So this is about a milliarc second and about 5 milliarc seconds per year. Then you have maybe 10 to the 8 lenses per square degree, fewer sources, but still a large number. And again, multiplying lots of large numbers by small numbers, you get about 40 to 4,000, depending on your source density, events per square degree per year. And then dividing that number through by the number of sources that you actually monitor, you get a few times 10 to the minus 5 events per year. So going back to the order of magnitude survey that we're doing, if you're getting a few times 10 to the minus 5 events per year per star, and you need 10,000 events, that means you need to monitor 200 million star years. So how achievable is that? So if you go and look, the Ogle microlensing survey has catalogs of the fields they observe online, and if you go and look at them and count up the number of stars in any given area, you come out at about 5 million stars that they can detect on their images per square degree. And if we run through this calculation for what a ground-based survey can achieve, Ogle has a 1 square degree imager, KMTNet has 4 square degree images. This is the kind of scale that you need. So for Ogle, you need to monitor 28 fields continuously for a year. If you run the survey longer, say 10 years rather than 1 year, you can reduce that number of fields down to what looks like a manageable number of 3. But this, recall that the detection efficiency I mentioned earlier was if you're observing continuously. If you're observing from the ground, that's obviously not possible. Your fields go behind the sun, you have weather, and you also have night and day cycles. So your observing efficiency or duty cycle is a lot less than 1. So if you account for that from one site, you'd need to monitor 500 1 square degree fields for a year, or 18 or so for 10 years. We also need to think about the timescales of observations involved. As we've learnt earlier in the week, the typical timescales are around a month for typical lenses. So it means that if you're going to do this effectively, you need to monitor your fields for a long period of time. But we're not interested necessarily in detecting stars, but planets. And we also learnt that the timescale goes as a square root of the mass. So extending this table from the key concepts document down to the masses that we're interested in, you get down to Neptune, Earth, and Mars mass objects, and they have typical Einstein timescales of fractions of a day down to a few hours, and in the case of Mars, less than an hour, the time for the source to cross the Einstein radius of the planet. So this, if you assume that the signal that you're going to see is going to be of order the Einstein timescale, it sets the cadence at which you must monitor your fields. There's another aspect you need to consider when thinking about timescales is you want to be able to resolve finite source effects for reasons we've again heard about, and then the source star crossing time for typical events in terms of the radii of the sources here is again on kind of similar orders of magnitude. So to cross the diameter of a G dwarf for a typical event is about 2 hours. For an M dwarf, it's about 1. So this is the duration of the planetary signals that you're going to see. So hours for Earth-mass planets, and you don't just want one data point in those. You need multiple data points to resolve the features. So that sets a cadence of about 15 minutes as a requirement for any survey to detect Earth-mass planets. So I'm not going to go through the exposure time calculation, but you need exposure times of a minute or two, and then you've got overheads, so you can only fit so many of those in a 15-minute cycle. So for the Ogle survey, the maximum number of fields that they could monitor is about 7, so falling short of the 18 you'd need for a good statistical sample. And this is the map of Ogle fields, color-coded by the cadence that they operate at. And the 3 red fields here are the ones that they operate at its highest 15-minute cadence. They spend roughly half of their entire time on these 3 fields, and then the fields with other colors are monitored at lower cadence. These lower cadences, you can find planets at higher masses because they have longer timescales. And you can also, and Ogle alerts their events, so you can also go and fill in some of the gaps in their cadence that way too. So how does this compare so we've done an order of magnitude calculation. We arrive at something that looks similar to the Ogle survey, at least what they can possibly achieve with the hardware that they have. But we've not found any truly Earth mass ratio planets from microlensing yet. We've got down to Earth masses, but with very low mass stars as hosts. So there's maybe 1 or 2 of those, and there's no very low mass ratio events. So how do the predictions compare? So Ogle 4, the phase that has its widest field camera, has been running for, I think, 6 years now. So we've either got 0 or maybe 2 planets, depending on how you count from this survey. And we'd have, if you'd multiplied through all the area that they monitor for the duration, you'd maybe expect 6. But this calculation was probably optimistic. I assumed that every star that they find in their images, they can monitor at high enough precision to detect Earths, and this is an optimistic assumption. There's probably a number of others in there as well. So it's coming out about right, at least at the order of magnitude level. The KMTNet survey is an improvement on Ogle in terms of area that it covers, and it also has telescopes at 3 different sites rather than just 1, so it can get continuous coverage. And that survey, you can maybe expect 20 Earths in a 10-year survey. Again, this is order of magnitude. There's a paper by Kalen Henderson that does actual simulations of this. And I think the number he comes up with is 50, but I could be misremembering that. So how do we improve on this? So this is a plot of cumulative stellar density, the line here, the solid line, in bulge fields. And per square degree, you get a few million stars that you can resolve from the ground. But we know that there's a lot more stars than the ones you can resolve. So if you can resolve everything, you get up to maybe 100 million stars per square degree. So the thing that's limiting ground-based surveys from actually resolving those stars is you have typical seeing of about 1 arcsecond. That disk has an area of about an arcsecond. And then you have 5 million stars per square degree so, that you're finding. So that corresponds to 0.4 arcseconds per seeing disk, roughly. And you can see this is a simulated image, but it looks very similar to the one I showed earlier, which was an actual local image. And essentially every other seeing disk, you have a star that you can see, which means that anything fainter than the magnitude at which you get to this number of stars, you struggle to resolve. And you can do photometry on varying objects that have that are fainter than this, but it's significant. The quality of it is significantly reduced. So if you go into space, you don't have to deal with seeing, and your resolution is set by the size of your mirror, not the atmosphere. And so for a 1 meter telescope, you can reduce the full width half max by about a factor of 4, which reduces the area of the seeing disk by a factor of over 10, which means you can get to densities much higher, so roughly 80 million stars per square degree rather than 5. And this is how you get up to the number of star years that you need to monitor. So just side by side, these are simulated fields of the exact same field simulated for the ground and the WFIRST. So you can see you're seeing many, many more stars in this space-based image than the ground-based image. So the requirements of a space-based survey to get at this 100 Earth number is you need a 1 meter or better telescope. You need to monitor this 200 million stars, which requires about 2.5 square degrees now. The cadence requirement is just the same. You need to resolve those features. So that puts you at a field of view of about a third of a square degree. And then you can achieve this in about 1 year of observations because you're monitoring the full 200 million stars. So what does WFIRST look like? It's, as Bertrand said, it's a 2.4 meter telescope. This isn't by design. The original designs for WFIRST were a 1 meter class telescope, but if you're given a 2 meter, why not use it? It's in the infrared with sensitivity that actually extends beyond bluer than 1 micron, even bluer than this, out to 2 microns. It has 18 4K by 4K detectors, which cover just about 0.3 square degrees, which is slightly smaller than the ideal, but you can only fit so many detectors in the focal plane. So this is close enough. The full width half max is better than you need for pure detections of microlensing events. I'll come back to why this is a good thing in a little bit. And then the mission is 5 years, but it's not dedicated to microlensing. Microlensing is only a part of it, so you have a roughly 1 year program of microlensing. Why in the infrared? Well, the main reason is there's a lot of dust towards the galactic center. So you want a high density of stars, and if you can peer through that dust, you can get a higher density per square degree. Also, there's a much lower sky background in the infrared compared to the ground. So infrared isn't optimal for for ground-based observers because you have such a high background, but that goes away once you're above the atmosphere. So you can push further into the red. And you can also get away with bigger pixels because your PSF full width half max is larger than for the equivalent mirror diameter. So that means you can cover a larger area in a given shot, and that turns out to be a good thing for microlensing. It might not necessarily trade off quite as well for other programs. But, so WFIRST is going to be in an L2 orbit. This is a great thing if you've ever dealt with scheduling Hubble observations or dealing with the systematics that it has. L2 is a much more firmly stable environment, and you don't have to deal with your field going behind the Earth at any time. The one trade-off, I think, is the lower data rate that you can achieve there, but that's surmountable. There's restrictions, excuse me, on where WFIRST can point. You need to power the spacecraft. It has solar panels, and you can only point those at a given angle to the sun. So this means the power requirements of a spacecraft and the thermal requirements as well mean you can only point within a range of about 72 degrees from the 90-degree angle to the sun. So that being as the year is roughly the same number of days as there are degrees in a full circle, that corresponds to a season length of 72 days. So going back to the timescales of events, we have a typical timescale of 30 days for a microlensing event. This means that it's long enough that you can monitor a significant fraction, if not all of a typical microlensing event, which is important for getting the parameters of that event out. And yeah, okay. So going back to the resolution element. So by having a space-based PSF of about 0.1, 0.2 arc seconds, this enables something that you can't do from seeing limited ground-based imaging. So we're typically used to not being able to resolve out the source and the lens of a microlensing event. But if you have high enough resolution imaging and you wait enough time, both the source and the lens are moving, so they'll eventually move far enough away from each other that you can start to resolve them. So 0.16 arc second full width half max combined with the typical proper motions, 5 milliarc seconds, isn't enough to completely resolve the stars. But what you can do is you can start to see elongation in the PSF of the lensing event if the lens is luminous. And from that you can measure the angular Einstein ring radius, and you can measure the flux of the lens star. Again, there's a number of other caveats. You need there not to be an interloper star that could be confusing you, either a companion to the source or the lens, or some other just randomly blended star. But under those assumptions, you can then use these mass distance relationships that you get a different one for each different measurement, either the flux or the angular Einstein ring radius, to solve the fundamental microlensing degeneracy and get out the lens mass and its distance. WFIRST is going to be highly accurate photometry compared to the ground. So there's, even in that short 72 days, and given its position in the orbit, there's a good chance you can get parallax measurements out of a large fraction of events. So we'll we'll probably have good cross checks on the flux measurements to make sure that we're not catastrophically failing, and to determine the rate at which those catastrophic failures happen. So what are the actual yields? So rather than just doing the order of magnitude, I've spent a lot of my time the past 6 years, even longer if you include Euclid work, simulating space-based microlensing surveys. I won't go into the details, you can ask me later. There's a number of caveats with these simulations. The design is constantly changing at this stage, and there's a number of physical uncertainties in the properties of the galaxy, and then you can need to worry about the planet populations as well. So the numbers are always uncertain, but they give you a good idea of what you can achieve. And so in terms of bound planets, these are the numbers if there was one planet per star. Obviously, this isn't the case for the largest mass planets, and we're going up into brown dwarfs here that you detect. But it's huge sensitivity to the mass function of planets. If you put in a measured mass function we have from the ground with some extrapolation, some conservative, or it was until fairly recently, conservative extrapolation into the to lower masses, you still get large numbers of planets. And this is for the latest design, so we're expecting about 150 ERPs. So this is assuming that there's 2 ERPs per dex in mass and semi-major axis. The Suzuki result constrains this to be, puts an upper limit that's lower than its value, but you're getting good statistics on the number of Earth mass planets, and and free floating planets you can do the same exercise and you get fewer of them, but again they're good statistics to measure the mass function of these objects. And I should say free floating planets is free floating and loosely bound, assuming that you've got no information on whether you detect them. So this planet population, when you put it in the mass semi-major axis plane, looks something like this. This is a rough and ready version of sort of the major plot that we show. It contains the lines here are roughly the sensitivity limit, and the blue points are a simulated population. And you can see that we're filling out a major portion of parameter space that isn't being covered by ground-based radial velocities or space-based transits from Kepler. So going back to the prettier version of its plot, you can also see that we're covering virtually all of the major solar system planets. So the planets in this region are the solar system planets, and then these smaller things at the bottom are solar system moons if they were isolated. And again, we're getting a large number of free-floating planets too. So just to give you a sense of scale for this, I like to show the radii, which they don't scale with the mass. They're a shallower function. So, but even we're detecting objects the size, potentially the objects the size of Ganymede, with WFIRST sensitivity, and this is how it compares to both Jupiter and the Earth. So it's really tiny objects. This is what the signals look like. So it's not a case of it being a detection right at your sensitivity limit. You get strong signals from these planets. It's the limiting factor in the number you detect is purely the detection efficiency. If you observe longer, you'll get more of these. So WFIRST will allow us to measure the abundance of cold sub-Earth planets, and what these actually are is they could be the failed cores of gas giant planets. So if if core accretion is how gas giants form, we expect solid cores to build up, and if they reach a critical mass before the gas disk goes away, then they will grow into gas giants. If they don't, then that critical mass is about Neptune mass. Then we know that most systems don't have gas giants like those in the solar system, so we might expect a good fraction of systems if the core accretion, at least the beginning stages of it, are efficient, then we'd expect a large number of objects below Neptune mass which didn't make it to become gas giants. And the power of WFIRST really can be demonstrated by what you get when you combine large numbers of planets like Kepler does. So this is one of the first occurrence rate papers from Kepler. And then if you combine that with the power to measure masses, not just mass ratios, in Kepler's case it was if you combined highly accurate stellar parameters, you can really resolve features in Kepler's case in the radius function of planets, but in WFIRST it will be going from plots that look like this, but this is a mass ratio occurrence rate plot. WFIRST automatically will get better number statistics on this and stretch it down to below even this axis. But the masses that you get from WFIRST will allow you to do to remove that convolving factor of the stellar mass and hopefully resolve features in the planet mass function, which is likely to be the physical variable that planet formation cares about. I mentioned free-floating planets. We can measure the total mass of objects that are free-floating and loosely bound down to an Earth mass per star over a very wide range of planet masses, from below moon mass up to Jupiter mass. And so this includes objects that would be in exo-Kuiper and exo-Oort clouds of other stars. And you can also possibly separate bound and unbound populations by looking for light at the position of the lens. And this is how that sensitivity compares to some models. So Elisa's going to talk about free-floating planet models later, and then here's some other models. And this was the measurement, the MOA measurement for free-floating planet planet objects from 2011. The number's wrong here. I can't remember where the new Ogle limit comes on this, but it's lower. Yeah. Okay. So yeah, if this model is correct for how many free-floating planets there should be, then WFIRST won't just be detecting, reaching limits at that kind of level. It will be detecting lots of them. So the other thing that WFIRST will be doing is it will be stretching the sensitivity of microlensing inward from where it currently is from the ground. This is just a detection efficiency effect for the main part, although the improved photometric sensitivity really helps too. So it means you can start looking into the habitable zone with microlensing observations too. So this is a plot of the colored bars here are Einstein radii from my simulations compared to the habitable zone, and they start to overlap or get close enough that you can detect things in the region of about 1 solar mass. So combining WFIRST detections in or near the habitable zone with the Kepler results, which aren't really getting great statistics in the habitable zone for solar mass stars. You can hopefully interpolate between the two results rather than extrapolating from one out, and measure the abundance of planets. So, and again, these are not small signals. So I've run out of time, but I won't go through this slide, but this is just a list of possible projects that I quickly thought of that need to be done for WFIRST. You don't need to look at them, you just need to see that there's a lot. And I think generally we're very open to newcomers wanting to work on WFIRST. That was an example of one. And then there's also a lot of projects that aren't WFIRST related. So if you don't like waiting for the thing you're working on to launch for 5 years or so, there's also plenty of stuff you can be doing now. So thank you. So by satellites you mean moons? Yeah. So at least in the plots I was showing, I was considering Ganymede as an isolated object, but at the position of Jupiter. In terms of exomoons, it's not exactly clear. The Galilean system isn't ideal for microlensing. The Einstein ring is roughly the size of the Hill radius of Jupiter, and so that means that everything is internal to Jupiter's Einstein radius, and the sensitivity when it comes to hierarchical triple systems like that drops a lot quicker than it would for just a two-body lens. So I'm not that hopeful about Jupiter kind of moons, but there would be systems that show up. Dave might be able to say a bit more about this. He's raising his hand. And then Trojans, I've got no idea whether you could, no good sense of how many you'd be able to detect simultaneously. So you'd probably run over the caustic of the Trojan, but miss the main planet caustic a lot of the time. Yeah. And you could also think about doing pre-covery with, so Euclid will launch before WFIRST, and if it took a snapshot of its region, then you'd have a longer baseline. And maybe I was speaking with Vukac earlier, and Gaia might be able to do something too. So.